Hello and welcome. My name is William, and today I wanted to share with you my procedure for measuring the resolution of some optical instruments. For this, we're not going to talk in MOA, minute of angle, but SOA, second of angle, which is, as you guess, 1/60th of one MOA. The rule of thumb in the industry is that one given instrument should be as accurate as the human eye at a given magnification. What does it mean? The visual acuity for the human eye with a perfect vision is 1 MOA, which means that 1 MOA is the smallest thing we can see with a perfect vision. And since 1 minute is 60 seconds, in 1 MOA, you find 60 SOA. Let's take, for example, a 1X system, just like, your normal red dot. For one instrument to be as good as the human eye, and you know that the more layer of glass, the less it will be able to resolve things at a distance. To be considered of good quality, this red dot should be able to resolve 60 SOA or 1 MOA if I look through it. Which means that if this optic was perfect, I shouldn't be losing any of my visual acuity looking through it. But when talking about an optic that is magnified, just like, for example, I can talk about this rangefinder, which is 10x, it means this optic should be 10 times more powerful than the human eye. Because if you magnify something 10 times, you should be able to see objects that are 10 times smaller than 1 MOA, right? So what is 1 MOA divided by 10? 6 SOA. So this rangefinder should be able to resolve objects as small as 6 SOA. And there's a very simple formula that tells you for one given instrument what should be its theoretical resolution. You divide 60 by its magnification. For a 1x optic, that's 60 divided by 1, so that's 60 SOA. For a 10x optic, 60 divided by 10, 6 SOA. If you have a 20x optic, that's 60 divided by 20, that's 3 SOA. If you want to dive deeper in this topic, I refer to one article that was published in the American Rifleman magazine of September 2005. I'll put the link in the description. But now the question is, so you've got your optic, how do you actually measure the resolution? The way people usually do it is through resolution charts. And me personally, I have chosen to rely on the US Air Force 1951 chart. Here is the one I use. So you see it's a very thin piece of glass with very, very thin lines printed on it. You can't print them with a normal printer. This is why these pieces are very expensive. It's because they use a process called lithography. So they're basically depositing some metallic elements on the glass. And this at microscopic level, it's so small that even if I try to look as close as possible, I can't see the closest group, the smallest group with my naked eyes. It's impossible. You need a microscope. This chart is made of groups of vertical and horizontal lines that get smaller and smaller. The way I usually do it is I set this chart, my target, on a tripod, and I set it at 25 yards away from my optic. Why 25 yards? That's because the minimum focus distance of most optics is around 25 yards. Ideally, you would like to bring your target as close as possible because even at 25 yards, you get interference from the atmosphere. So ideally, I would make my measurements in a well-lit warehouse, but I don't have one, so the best I can do is try outdoors. And with this chart, because I know the thickness of the lines in micrometers, I know how many SOA are each lines at a given distance. It's exactly the same thing as the concept of 1 inch at 100 yards for 1 MOA. With my calculations, I have produced this chart, so I know that 1 MOA is exactly 1.047 inches at 100 yards. So 1 SOA you divide by 60 is 0.01745 inches at 100 yards. If you want to know the apparent angle at 25 yards, you divide by 4, that's 0.004363 inches. And because the size of the lines on my chart is given in micrometers, you need to convert this in micrometers. 1 micrometer is 1,000th of a millimeter, so that's 1108 micrometers at 25 yards. But because we are measuring resolution with line pairs, this 1 SOA is the total thickness of one black line and one white line. It's basically the black line and the blank above it. So for your instrument to resolve one SOA, it means you divide by 2. That's 554 micrometers. Let me run you through one example with a very high quality optical instrument, which is my camera with which I'm filming myself. So for this particular test, I've taken my Canon R3 with a 135mm lens. If you are familiar with DSLRs and mirrorless, you know that 1x is at 50mm, so 135mm is 2.7x. If I do the maths, it means it should resolve 22.2 SOA. But the good news is that this lens focuses at much shorter distances than a spotting scope. So after some more maths, it should be able to resolve 76.9 micrometers, and this at 1.43 meters. What does it mean on the chart? It means that it should be able to resolve Group 2, Element 5. But what does it mean, able to resolve? There is no consensus about what resolving means in terms of contrast. So to make things simple, I said it's subjective. I say that able to resolve means I am able to count the number of lines in each group without any problems. So once I take the picture, I check it on my computer, and here I am seeing that it is able to resolve not only Group 2 Element 5, but also Element 6, which means it exceeds what the eye can see. However, there's limitations because the US Air Force 1951 chart does not give us the ability to automatically measure everything, let's say chromatic aberrations, contrast, or the amount of light that goes through an optic. But as a shooter, I'm not going to bother with all these variables. It's very simple. If I can see and clearly count the number of lines on the chart, for me, that's mission accomplished. The way I do it with my other optics is I take 2 sets of measurements. The first set is through my eye. I look through my optic and I write down what is the smallest group I can see with my eyes. But because my vision is not perfect and I want something replicable, instead of my eyes for a second set of measurements, I use my camera and check on the computer what is the smallest group that my camera can resolve. The problem is, depending on the circumstances, the human eye is much more tolerant to imperfections compared to a camera. So a scope that appears very sharp to the eye might exhibit chromatic aberrations, distortion, astigmatism, loss of contrast when you take a picture with a camera. So it happens that sometimes I get better measurements with my eye and sometimes I get better measurements with the camera. When I finally get my sets of measurements, I compare them with the theoretical value. So remember, my rangefinder should be able to resolve 6 SOA. But through some tests, I realized that it's only able to resolve 9 SOA. So I divide these 2 results to get a divergence factor. So if you divide 9 by 6, that's 1.5. If you get a divergence factor of 1, it means your optic is perfect. I found out that if you get a divergence factor of 1.2, it is still acceptable. If you have something between 1.2 and 1.5, this is still decent, but not perfect, meaning that you can see less than what you should be able to. But beyond 1.5, I think the loss of quality becomes very noticeable. And let's say in a variable optic system, you are better staying at a lower magnification because it means you don't gain anything by increasing the magnification. But even if you have a perfect optical system, it doesn't mean you can do everything with it. Let's take an example. I have a spotting scope that can resolve 2.26 SOA at 45x. So one day at the range, I'm shooting 308 and I'm wondering what is the maximum distance I can spot holes in the paper targets with my spotting scope. If you do the mathematical calculations, you know that a 308 bullet produces a 17.2 SOA hole at 100 yards, but these holes are 2.45 SOA at 700 yards and 2.2 at 800, which means that if I take my spotting scope, the furthest I should be able to spot these holes is around 700 yards. But is it actually the case? Of course not. In practice, I've realized that with my spotting scope, the maximum distance on average I can see these holes is 300 yards. Why? That's because of the atmosphere. especially on a shooting range where you have a very high gradient of temperature, the ground is very, very warm, and if you have a little bit of wind, that's enough turbulence for your target to be completely blurry. Even if you have a perfect optic, sometimes the atmosphere plays against you. I hope this video was useful. Thank you very much for watching, and stay safe out there.